Oh, leave.
Yeah,
Yeah.
I just take a function. They have a small this one.
Okay, I think we're going to get started. I'm really excited to introduce our next speaker. Anca Dragan is here, local. She's at Berkeley and is a new assistant professor, and is going to tell us about some of the work they're doing in interactive robot learning.
Thanks, Andrea. Hi, everyone. Thanks for the invite. So I'm primarily a roboticist, and I've spent a lot of my time worrying about robot objective functions and how to create robot objective functions. So a very brief 1-minute guided journey is that back towards all the way the beginning of my PhD, I was working on trajectory optimization. So this is a problem when you're trying to find a trajectory from a start to a goal that avoids obstacles. And you would like some planner that smoothly bends the trajectory out of collisions. And so you have two things that you care about. You care about staying as far away from obstacles as you can, and you care about being as smooth and as efficient as you can. Then those two are at odds with each other. And so you have to figure out how to trade off between them. And of course, you can think about hard constraints and so on. But that was one of the things that was the main kind of bottleneck of this whole thing. And then things got even worse from there, because I then moved into a world where what is the right kind of objective function wasn't something objective, was something dictated by the end user. And so we were working on a shared autonomy kind of project where the robot was trying to infer what the operator wanted to do, and then try to figure out how to assist the person. And there the robot had its own trade-off to make between doing what the person literally said to do and doing what it thought the person wants it to do. And again, different people wanted different things there. And then I moved on to making robots move in a more intent-expressive way. And so again, there we cared about intent expression as a feature of the motion, but we also cared about things like efficiency as a feature of the motion, and again ran into trade-offs. And so you can kind of see the story going. Recently at Berkeley, I got more and more involved with autonomous driving, and there is not just 2 or 3 things that you care about. You care about many, many different things, and it becomes sort of a mess to try to figure out how to trade off between them, and so on and so forth. So this is all not surprising, because I remember back in the day when I wrote the Russell and Norvig AI book, they had this beautiful example of how hard it is to write down objective functions for robots. And the example that they gave was that of a robot vacuum cleaner. They said, look, imagine you have a robot vacuum cleaner. A fairly reasonable objective function you might write down is to give it a reward for sucking in dust, right? The more dust it sucks, the better it is. And so then they showed that the optimal policy for this is one where the robot sucks in some dust, but then instead of going off and collecting other dust from other places in your house, it just dumps the dust and then sucks it again, right? So it just goes in this loop. That's an example of that's not what we want the robot to do, but it's the behavior that emerges out of something that at the first glance seems like a very reasonable objective function to write down. And so inspired by kind of these struggles of trying to formulate objective functions, trying to write down objective functions for robots, we've spent in my lab the last year or so thinking about this problem of how do I learn, how do I come up with these things that are in people's heads implicitly, but they can't explicitly write down, at least not very easily, it seems. What's a way for robots to do that? And I just want to point out that we're thinking about this for 2 very important reasons. One is to be able to make the robot, like we were saying, act in the way that the person actually wants it to act. And then the second reason is that we want these robots to interact with people. So learning objective functions that people have kind of in their head implicitly is also a good way to start figuring out how people are going to behave in new situations so that you're able to interact with them. So to kind of ground this in an example, it's a bit like saying we want to be able to learn objective functions, both so that we can enable, for instance, a car to drive according to the passenger preferences. That's one reason to try to learn the objective function that a person has in their head for how they want the robot to act. But it's also interesting to think about learning objective functions that people might implicitly have in their head to be able to actually predict how people will drive, right? So if I want to interact on the road with people, with human-driven vehicles, then we might want to discover or learn what objective function drives their behavior so that we can actually predict what they're going to do in new situations where we're them on the road. Now, of course, there's an established way of doing this, and it's called inverse reinforcement learning. So I think most of you know about inverse reinforcement learning. The idea is that you have a person, and the person implicitly knows some parameters, the parameters of the objective function that we're going to call theta, and but again, can't explicate them, can't write them down. But what they can do is they can act approximately optimally according to them. So the person can demonstrate behavior where the probability of the person taking one particular trajectory, for instance, is higher when the behavior is less costly with respect to their underlying utility function. So, and this is just one way of formulating that. It comes from the principle of maximum entropy. And so that's the kind of core assumption in inverse reinforcement learning. You're going to have an expert that can't write down this data, but they can act approximately optimally according to it. And we're going to have a robot observer who gets to see the person's actions and know that the person's actions can be literally the person acting, or they could be the person actually operating the robot and telling the robot what to do. I'm sure you're going to see some talks on Wednesday on that sort of interface as well. But regardless, the robot from the autonomy side is sort of sitting there observing these controls, these actions from the person, and is trying to figure out what theta is underlying these actions, right? So one way to think about this is you're trying to find the theta that explains the data that you've seen, doing a maximum likelihood estimation. Or more generally, you can think of the robot taking these demonstrations, these actions for the person as evidence about the person, the underlying theta, and running a Bayesian belief update on this space of parameters. So that's inverse reinforcement learning in a nutshell. It's been very, very successful because it can represent behavior in this very, very compact way in the form of a reward function that's kind of underlying that behavior. So that's pretty cool, and we've been using it a lot in our driving work. But sort of the more we thought about inverse reinforcement learning, the more we realized that it is implicitly making two assumptions that we might not necessarily want to be making. So the first assumption that inverse reinforcement learning is implicitly making is that our robot here, at least during the learning phase, is a passive observer. The robot sort of sits there, observes the behavior, and then goes off and learns and then acts according to the learned behavior. And robots are robots because they're actuated. They're actual agents who can take physical actions in the world. And so it might be useful to start thinking about leveraging this in order to improve learning. And I found, I think I'm preaching to the choir here, but I found a glorious video on the internet to exemplify this. So the idea is sort of that you can, all you could do is actually observe this turtle, right? And you try to figure out what kind of turtle it is. You might go throughout your life thinking that it's a very nice, gentle little turtle, even though maybe it looks a little weird, but regular turtle. But if you actually get to take physical actions that probe at the turtle, then you might quickly realize that it's this, raging ball of destruction. I don't know what kind of turtle that is, by the way. So this is sort of suggests that passively observing the world is okay, but to really get information, in some cases, it might be actually useful to act, right, to take action. So we might say that inverse reinforcement learning is great, but maybe one desiderata is that if we have robots who can act, we should be able to leverage these actions to improve learning. So that's the first assumption, that robots are passive observers that we might want to change. The second assumption is a little weird, but essentially when we're doing inverse reinforcement learning, we're implicitly asking people to behave like uninterested experts. And here's what I mean by that. So we're asking people to behave optimally according to their theta. And that's a little bit like trying to learn gymnastics by watching Gabby Douglas. Or when I learned how to drive from my significant other. He drives like a maniac. Watching him drive in his expertly way wasn't exactly that useful for me, right? And I think I'm preaching to the choir. What's useful for me is, because I had the skill level that looked something like this, right? So I was not ready to observe the way he drives and make anything out of it. He kind of had to dumb it down for me and bring it down to my level. And similarly, we don't learn gymnastics by watching Gabby Douglas perform. We learn gymnastics by getting coaches who kind of break down the task, emphasize certain things, right? They coach. They are not just uninterested experts. So perhaps the second desiderata is that we shouldn't be asking people to act in their expertly ways. We should be asking people to explicitly try to teach these robots, and robots should actually embrace that and sort of take advantage of that. And so those are the two things that we found. And then we started thinking of, okay, well, inverse reinforcement learning doesn't satisfy these. Is there a problem formulation that might, where if you solve that problem, these sort of things just emerge out of the optimal solution? And so what we did is we ended up formulating learning as a cooperative two-player game. And so the idea is that you make it a game so that you have two agents and they both take actions. You don't have someone who's acting and someone who's observing. And you make it cooperative so that you actually give the person an interest into the robot's learning. So when we go back to inverse reinforcement, all right, let me try to fix that. Hopefully that will be okay. All right, so when we go back to inverse reinforcement learning, what we decided to do is, first step is now you have two agents and they can both take actions in the physical world. You could formulate it in such a way that these actions are not independent of each other. They're coupled, and they're coupled through the objective functions that these two agents have. So the person has their objective function, but importantly, how much payoff the person gets depends on what the robot decides to do as well. And the robot might have its own objective function. So that's nice, because now you have a robot that, in order to figure out what to do, it should have information about theta. And then you can go a step further and make this cooperative and say, well, actually, both agents are going to get payoffs according to the same utility function. So now it's an actual cooperative game that they're playing together. And so if you were to solve this, what you would get is a tuple of policies, one for the human and one for the robot, that have these nice properties where the robot would actually act to try to improve its estimation, because in order for the robot to do well, it needs to know what theta is. And not only that, but the person will try to help the robot get a good estimation, because the person gets better payoff if the robot actually knows what it's doing. And so that was really nice. We thought of this, we said, yay, success, but then, of course, there's the challenge of tractability to consider, which is how on earth would we actually solve this type of game? Inverse reinforcement learning is really one approximation that you can make to be able to solve this tractably, and the approximation is in particular that we're going to fix the human's policy to be an expert demonstration, and we're going to have the robot compute what in game theoretic terms would be called a best response to the human's policy. where the robot basically assumes that there's not going to be any more information from the person after they see the person's trajectory. And then the robot does its Bayesian belief update and then proceeds according to that belief distribution going forward. And so that's what we do in inverse reinforcement learning. But then setting it up as this game sort of enables us to think about what are other approximations that we could make that maybe take us a little bit closer to these desiderata that we have about robots acting and about people. Yeah, question over there.
When you're talking about cooperative games, is it really a cooperative game? Because then we need to define the solution concept. Or is it really, when you're doing best response, it looks like an uncooperative game. And you're looking for a stable point, which is like a Nash equilibrium.
So if you were to solve the original cooperative game, you would get a tuple of policies that are a Nash equilibrium, right? But what we're saying is that
Cooperative, if it's Nash. Okay, in cooperative games,
they're just their best responses to each other, but their best responses according to the same utility function, and so everyone's happy. And so it's in particular the equilibrium that has the highest utility, right? That's all we're saying.
because cooperative game has a core as a solution, so, and not best response, but that's fine, maybe.
Right, so this is so first we set up a cooperative game. We said here, you could potentially solve this, but it's not tractable. And here we're just pointing out that inverse reinforcement learning is a very rough way of approximating a solution, where you're basically saying, I'm not going to actually solve the game. I'm going to commit to a policy for the person, and the person's going to act as an expert. And the robot is going to assume that it's going to just see the person act and then stop getting information. And so then the robot will do the thing that's the best for it to do, which means estimate that theta based on the demonstration that you've seen, and then act according to that. So that's just how inverse reinforcement learning relates to this original game, right? It's not the solution to the game in any way. In fact, it very explicitly assumes fixes the person's policy to something that we'll see in a little bit is not the optimal thing to do in the game. But now that we can understand inverse reinforcement learning in the context of this type of game setup, we can think of what are other kind of approximations that we could do that are maybe a little bit better, right? Again, we're not going to fully solve the game, at least not in continuous state and action spaces, but we might be able to have an approximate solution that actually gets closer to the desiderata that we have. And so there are two important parts of that, right? So there's actually making it a game, namely the robot is now a player too and gets to act. And the second part is the cooperative part. And so I want to kind of first we're going to go into, and I'm going to share a little bit with you on the game part, and then I'm going to share a little bit with you on the cooperative part. So first, when it comes to the game side, and the particular sort of domain that we're going to have in mind here is in particular a domain in autonomous driving, where the reason we want to estimate this theta that is internal to the person is because we're assuming that the person acts according to it, and we want to be able to use this as a way to actually interact with people on the road, be able to anticipate what they're going to do so that we know what the robot should do. And it's important to be able to do this kind of as an ongoing interaction, because different people drive in very different ways, right? So you see a new driver, maybe at a new time of day, they're probably going to drive in a slightly different way than the drivers that you've seen before. In particular, there are people who are more aggressive, more distracted, and so on and so forth, right? So you can think of them as, you can think of all these driving styles as parameterizing having some particular theta that corresponds to this. Maybe the aggressive driver puts a very low weight on safety compared to efficiency, right, and so on. Okay. So going back to this approximation that the inverse reinforcement learning makes, we're going to make a slight improvement to this, and we're going to make the, sorry, I just want to skip ahead to something. Okay, So this is what, there we go. This is what inverse reinforcement learning did, right? And so if we apply inverse reinforcement learning directly in this setting, let's say that you're on the road and you're trying to, as you drive next to this person, figure out what is their internal theta, right? Is this person an aggressive driver? Are they paying attention or not? What is going on with them, so that you know how to interact with them. And so the first thing that we notice is that if you're just driving next to them, unfortunately, and you're keep on updating your belief based on the actions that they keep on taking, right? You have an observation model for that, everything's great, but you're not actually getting a lot of information. Because for the most part, aggressive versus defensive drivers who are paying attention, drivers who are not paying attention, they're kind of driving in the same way when you're not sort of messing with them in any way. And so, so if the robot just does inverse reinforcement learning here, then it's not going to get a lot of information. And what we notice happens in this type of example, for instance, is that if the robot, for instance, needed to merge left, it would have no choice but to let the person through first if it doesn't have enough kind of gap in traffic to merge in front of them, let the person through and merge behind, right? So this is the typical behavior that you see in autonomous cars today, where they're sort of very defensive, they're waiting for everyone to go, and then they finally kind of get to creep in. But that's not what we do, right? So I drive on the Bay Bridge to get here every day, and I drive home every day when everyone's trying to get into the city. And every single day I have to do something like this to actually make my way home, right? I have to actually stick myself in front of people and force them to have some sort of reaction to what I'm doing, right? Namely, hit the brake and make a little bit of space for me. And if we don't do things like this, then the robots get stuck, essentially. This is one of the best articles on the matter. It's an article from back, I think it was a couple of years ago, where the Google self-driving car got stuck at an intersection because people kept on inching forward into the intersection. And there was never a big enough gap to actually go through, so the car was just there and hung out until the driver finally took over. And so, so this is kind of what happened. Sorry, what?
Was there a person at the wheel?
There's a person at the wheel. So the way they work is they only intervene when something is about to happen. So they didn't intervene for a while.
Normally people are sort of polite, right? And then if there was a person there, they would have probably surprising.
Yeah. Well, so this is what happened. And you know, similarly, kind of what going back to the Bay Bridge situation is the kind of thing where it's very polite to let everyone go through, but at some point, you know, you need to go home, and so you need to sort of insert yourself at some point in traffic. So basically what we did here is we thought, well, what if we improve this a little bit, and instead of you know, just observing the person's actions and computing the best response to that, what if, you know, we explicitly allow the robot to act, and we explicitly think about, so if we allow the robot to act, then all of a sudden what the person does also depends explicitly on what the robot decides to do, and that changes the observation model that the robot has, and now we have an opportunity to do something that I think happens a lot in this community, which is to actually actively learn, right? To actually gather information. So we can decide on actions to take that explicitly incentivize information gain about this belief, right? And it's explicitly because depending on what the robot does, you'll see the person doing different things, and some things can be more informative than others. And so, of course, we can't compute this directly. We have to actually take an expectation over our belief over theta, because we don't actually know what theta is. Therefore, we don't know what observations we're going to receive. And so, but this is one way to set up the problem where, again, we're not solving the full game. We're just saying, look, the person is still going to be fixed to a policy, to an expert policy, just like it was in reinforcement learning. But now we're going to just allow the robot to act and see what the robot can do in order to actually gather more information about the person's utility.
Question?
Yeah.
Could you explain this objective, the entropy base?
Just information gain about the robot's belief on theta.
Do you mean like an absolute value of the difference? Because otherwise, if it's a complete Bayesian model, the expectation is the same. Right. So if it's an unbiased model, then h of b and h of b prime are the same. No?
As
you are. So if you take like an absolute value or a squared value, I can see like you're maximizing the variance given you are.
all I'm saying is, and correct me if I'm wrong, but all I'm trying to say is, look, if I got an update, right, and I went from B, my prior, to B prime, my posterior, those things are going to have different amounts of entropy. For instance, my prior might be completely uniform, but after I've gotten some evidence, for instance, the person hit the brake in some way, now I actually know that I have much more probability mass on the person actually paying attention, for instance, and so my belief distribution is going to have lower entropy. And overall, what the robot is trying to do is figure out actions that it can take so that in expectations, it reduces the entropy as much as it can.
Oh, so to make the other person predictable.
Yeah.
Okay.
Right, so the robot is trying to estimate this. It holds a belief over that, right? So far, what we were doing is we were just saying, okay, I'm going to drive the way I would normally drive, right? And the person's going to act alongside me. And I'm going to use their actions to update my probability distribution over their driving style, their internal utility, right? And so that worked fine, except, you know, this thing happened that we saw here, which is that you get the same observations regardless of what theta is, right? You can have a theta that stands for a very aggressive person, a theta that stands for a very defensive person. They do the same thing. And so you don't actually get to collapse your belief at all. And so here the idea was very simple, and it's something that you see in active learning a lot. But it's okay, since I get to actually act, I can be a little bit smarter about the way I choose my action so that I aid learning. That's all that's happening here, right? So that I try to instigate. Essentially what's going to happen, right, is that the robot is going to try to figure out something to do such that if the person were, say, attentive, they would react very differently than if the person were, say, distracted. Right? That's the kind of thing that will actually give you information and expectation. Whereas just driving along them in a regular way is not so great because, you know, they're going to act in the same way. So in expectation, that has low information gain.
Well, is that action different than what you would do if you're trying to maximize, the robot was trying to maximize its immediate utility? Because I think when I try to drive, I'm going to probably just, you know, try to go zoom left because that's going to maximize my immediate utility. And maybe it also gives me information.
Yeah.
But I'm not actually doing information maximization, I'm doing
Yep. So when the robot is trying to just maximize, so this was actually the situation from before when the robot was actually just trying to maximize its own selfish utility. It's just that it needs to decide on what to do based on what it thinks that the person will do as well. So if it's uncertain about whether the person is paying attention or not, for instance, right, it won't just go. Because if it just goes, it has a 50% chance that the person will just run into them, right? So that's a bad plan for the robot. And so when it's planning using its best estimate, right, or using the whole probability distribution over the person's model, what it decides to do is to slow down and go behind the person if it actually needs to merge. And that's because that's the safe thing to do. It takes a little longer time for it to achieve its destination, but there's not a 50% chance that we'll collide with the person, right? So that's what's happening there. And so what we're comparing here is really, and thank you for that question, because I should clarify, what we're comparing here is a model where the robot is solely optimizing for its selfish utility versus what we really do here is we trade off, right, between optimizing for my selfish utility exploit mode, right, using my current estimate, and this information gathering term. And really, you can see this whole thing as a POMDP, and if you were to solve it as a POMDP, everything would be fine. The robot's policy would automatically trade off in the right way, but we can't solve POMDPs very well in continuous state and action spaces, and so we kind of formulated the problem as, okay, you're going to keep on optimizing for your selfish reward according to your current estimate, but we're actually going to try to get you to get more information, and that will help overall with the reward optimization. This is not at all a new idea. It's actually been used in navigation and a lot in manipulation, where, for instance, robots try to figure out what actions to take in order to actually localize something, right? So you poke at an object in different ways and touch it in order to figure out where it is. What's kind of interesting here is that we're doing it over not the physical state, but the human internal state, right? And the dynamics of that are a little bit more complicated than the dynamics we get in manipulation. So in particular, this is the optimization that we set up, which is equivalent to this here. So to kind of even evaluate this, you have to kind of say, okay, if I have a UR and I want to figure out how good that UR is in terms of the expected information gain, well, I have to think of every possible parameter of every possible value that theta could get, and for every possible value that theta could get, I have a probability distribution over what the person might do. And if I have this probability distribution for everything that the person might do, I can figure out what my B prime would be if the person actually did this. So this is, even just evaluating is computationally difficult. And so we're making here several approximations in order to be able to solve this in close to real time. And so the first thing we do is we actually going to close our eyes and assume that we're going to observe the optimal behavior. So instead of drawing from the whole distribution and considering all the possible things that the person might do, right, we're just going to pretend like we're going to get the maximum likelihood observation. And then the other thing we do is we run model predictive control. So instead of solving this for the full time horizon that we actually care about, we're actually solving it for a finite time horizon, executing the first action right in that plan, and then running MPC again. Now, the final thing we do is we do a quasi-Newton method. So even with model predictive control, even if you plan for a short time horizon, this is still continuous state in action, and it still requires doing this computation. And so, so we do a local optimization. Kind of what's interesting here is that a local optimization relies on being able to get a gradient of this, and getting a gradient of this relies on being able to get the gradient of sort of this guy, UH star, so to say, the thing that the person would optimally do with respect to UR. And so here we were able to use implicit differentiation to get an actual formula for that gradient. But it tells us as I perturb UR, how will the optimal thing for the that a person would do get perturbed. And then finally, we go from an integral into a sum because we don't know what else to do. But if you have ideas, I would really appreciate that. So basically, instead of looking at all the possible, the whole space, the whole hypothesis space of possible utility functions, we sort of offline do some kind of magic clustering of user types. And online, we just identify what type the person is as opposed to. So this feels a little cheap, but I don't know what else to do with that equation. So here's what happens. So kind of back to the situation where the robot is trying to, yeah.
Any parameters of the human that you use for this type of clustering or modeling the groups of human behaviors?
So far we did something really, really naive. I think what you would ideally want to do if you're going to go the discrete number of possible reward functions way is, well, first you collect data from a lot of people. You learn a reward function offline for each person, and then you try to figure out what distance metric to use in the space of reward functions to be able to say whether people are similar or not. And possibly you don't use Euclidean distance in reward parameters, you use the effect of optimizing for that utility function on the environment. We haven't done that yet, but I think that, you know, if you're going to go that direction, that's probably the way to go. It also feels like if I could not discretize this, I would prefer not to. I just don't know how to approximate that integral. So despite all of this gazillion approximations that we need to do, right? Here's what we're getting compared to just running passive estimation, passive inverse reinforcement learning. The robot actually miraculously decides to nudge into the person's lane. So it's not committing to a merge, it just sort of nudges in a little. And if the person is distracted, that's okay, it kind of goes back. And so if the person is distracted, that means that the person will keep on going. That means that its belief will get updated to have more probability mass on the fact that the person is distracted, because an attentive person would have brake. At least that's what its model says. And so tough life. But if the person is actually paying attention, it will go ahead and complete the merge, because it will get this, this belief update. They say, OK, the person is actually paying attention. And now we can do what Emma suggested, which is, OK, now it's actually safe to merge in front of the person. So that's nice. Even nicer is actually what happens at these four-way stops. So kind of going back to the example of cars getting stuck. So what the car decides to do is, at an intersection, is it decides to inch forward into the intersection. And that's a sort of information gathering mechanism. And it decides to inch forward because they're kind of going back to your points. This is what people do, right? They very nicely cluster. You're going to see one behavior from distracted users and a very different behavior from attentive users. And that will give you, despite the fact that the observation model is soft, right, is a probability distribution, you're going to get enough information to actually be fairly confident in the type of driver that you're dealing with. And so there's really this gap that's magical, and it exciting. How much time do I have, Andrea? OK, there we were. OK, so, and that, here what you see plotted is the robot's belief in sort of the kind of passive case, and in the case where it gets to act to gather information. Interestingly, we also looked at what the robot did, right? So the robot's trajectories are very different when it's dealing with distracted users versus attentive users. And this was really cool to see. So the robot decides to inch forward, and if the person is actually paying attention, then the person behaves in one way, they stop, and then the robot just continues through the intersection. That's sort of the upper part of the curve. The other part of the curve that you see is if the person is distracted and they're keeping on going, they're not reacting to the robot inching forward, then the robot nicely backs up and lets them go through. And the plots that you saw were actually generated from user studies now, admittedly in a very janky simulator, not in a real world driving scenario, but these were real people kind of off the street that were interacting with these kind of planners. And it's really exciting to me because it kind of brings us back to this, where in order to interact properly with people, you can't really treat them as obstacles, and you can't really just assume a universal model of how they drive to make your predictions. You actually have to interact with them to figure out more. And it's really nice that this interaction model, even though it's not too different from inverse reinforcement learning, it just enables the robot to act and gather information, actually results in these behaviors that we look at, and they look at like actual coordination behaviors that we'd want to see. And we don't have to hand code them anymore, right? No engineer has to sit down and say, oh, OK, inch forward at an intersection by about this much, and not this kind of intersection, but this other one, and so on. And the planner figures that out. You had a question?
The robot's action influenced by whether it thinks it has the right of way, or does it learn to ignore that?
That's a very good question. In our simulations, we don't really put in constraints about right of way and so on. And so this is a particular model from four-way stops in most, not most, but a lot of cities or states in the US where there's the person on the right has right of way. If you arrive at about the same time, you have to play the kind of coordination game of do I go, do you go? So this is the kind of situation we were trying to test.
The other person arrives clearly earlier, they still try to beat them to it.
No, I mean, it will just do whatever is, and it depends a lot on the trade-off that you set, right, between information gathering and just exploiting your reward function. But so you have to reason a little bit about value of information here and set that trade-off accordingly. But ideally, it will just let the person go through if they arrive significantly earlier, because that's the optimal thing to do, regardless of what driving style they have. Yeah.
What if two of your robots is actually?
Yeah, I don't know. This is explicitly what we do to interact with people, right? So when we interact with robots, we probably don't want to follow this type of interaction model, right? We probably want to really think of it as fully a game, and we want to model what the other robot is doing. Are they arriving at a Nash equilibrium or not? Know that this is not the cooperative case. This is very much, you have different utilities, and you have to reason about it in a different way. What we found is that this approximation of people essentially not necessarily going all the way to a Nash equilibria, but computing a best response to whatever the robot is doing, is something that works fairly well in kind of day-to-day interactions. And there's some evidence out there that people don't actually fully solve games when they're just out and about. But sometimes they do, right? OK, so this was all I need to end, so I'll skip some things. I was going to quickly mention that when it comes to this other side of learning how the passenger wants the car to drive, then you're all of a sudden in the more regular active learning setting where you don't necessarily take physical actions, but you can make queries. And what's interesting about this space is that our queries, so we're looking at this type of queries where you can ask the person to experience two different trajectories and say which one they would prefer, and that gives you information about their preferences. But what's interesting here is that you don't rely on a discrete set of queries that you're looking for to figure out what to ask, but you can actually generate them using the same kind of techniques directly from the continuous space. So that's on acting to improve estimation. I guess I'll just take 2 minutes if that's OK, Andrea, to talk about sort of the flip side, and just mention that so far we've talked about driving, where the human and the robot have different utilities. When you make this an actual cooperation, what ends up happening, I'm going to skip through some things, is that the person is going to, for instance, try to come up with the best thing for this is the algorithmic teaching perspective. The person is going to try to figure out how the robot is learning and figure out what demonstration they should provide. That's not necessarily the expert demonstration, but it actually helps the robot that is running inverse reinforcement learning perform well. And so it's pretty easy to show that an expert demonstration is different from sort of the best response to the best response that the robot would be computing. So this is kind of inverse reinforcement learning. And now if you're wondering what should I show the robot if I want to teach it, that's going to be different. And we only have toy examples in this domain, but the toy example goes something like this. Imagine this is the true reward function. So there's these peaks, and the robot knows about these peaks. But what the robot doesn't know is their relative value, right? So which ones are good, which ones are bad. And imagine this is your starting state. And if you get an expert demonstration, what the expert will do is they will go straight to the closest peak, the closest good peak, right? White, I should say, was good. So there were two white peaks and one black peak, and the robot would just go, the person would just go to the closest white peak. And you don't actually, I think I'm going to give up on this computer and just share this with you myself. So the two white peaks, one black peak, an expert demonstrator would just go to the closest white peak and hang out there. The kind of best response to an inverse reinforcement learner would actually visit both, because that actually gives the robot evidence that this other peak that wasn't visited in the expert demonstration is also a good peak. And so it's a very, very simple little toy example, right? But it suggests that you can start creating teaching demonstrations And then the other thing I was going to share with you is that this actually makes a statement about what kind of inverse reinforcement learners are more easy to teach. In other words, what this hinges on is this observation model that the robot assumes that the person is using to produce the trajectories. And so what we find is that there's a little bit of a sweet spot where if you assume that the person is perfectly optimal, there's very little the person can do, because deviating from that basically negates everything. It says probability 0 to any reward function that wouldn't have produced that. And then at the other extreme, if the robot assumes that the person is very noisy, right, then that's also bad. You don't get a lot of information. So there's some sweet spot in the middle that kind of, the robot has enough flexibility in the observation model that enables the person to take kind of interesting teaching actions that best illustrate what's happening. So kind of this shows that we have to be, even if we're running inverse reinforcement learning on the robot side, we have to be a little bit careful about what we're assuming in the observation model underlying that. So that's basically it. We're also doing some interesting things on trying to not assume that the person knows how the robot learns, but trying to give the person a good mental model of the learner and what the current robot belief over theta is. So I'm excited about that, and that falls squarely under algorithmic teaching. And just kind of to pop back, I'm excited about the fact that you no longer have a person giving you a demonstration. Still one person, one robot, but you don't have a person that is an uninterested expert giving you a demonstration and then a robot that passively observes what's going on, but you're trying to actually have an interactive process. And even though there's many approximations involved and so on, I think we're seeing some evidence that looking at the problem this way can actually significantly speed up learning. That's all. Thank you. Sorry for all the technical problems.
We can take a couple questions while we switch speakers. We'll have more questions for Anca.
How do you balance gathering information with safety?
Yeah, so how do you balance gathering information with safety? So the safety part is in the robot's reward, right? And the robot is trading off between gathering information and exploiting its kind of selfish reward function. And there are some techniques that look at adapting this trade-off over time, right? So and what I've showed so far, we just set it to something, and that's clearly the wrong thing to do, right? You want to be able to reason about the value of that information that you would gain, would it really change the plan that you would come up with? So those are things to sort of think about. And there's a community, and within approximating POMDPs that has thought about that sort of thing. Mm-hmm.
Better do you think it could get? So you're sort of thinking about these different approximations to the ultimate sort of objective you'd like, and so IRL is one, which is fairly simple, and you've already seen pretty significant gains.
Yeah.
Do you have a sense of what other relaxations or what other improvements would lead to substantial?
Besides the two things that we've managed to look at, I think that's a great question. If we could solve the game tractably, I don't think that that's the right thing to do anyway, because I don't think that that's what they would model the person as solving the game perfectly as well, and that doesn't really happen, right? And so I think it's a question of the robot learner being different, the robot learner relaxing the assumption that I think the game already is making a lot of assumptions about the person actually having perfect knowledge. Let me say it this way, the only missing knowledge is on the robot side, and the person has perfect information. And that's not truly the case, so there's kind of parts of the state there that we're missing. The person has its own beliefs over things, and I think that would be a really big bang for the buck. I don't sense that kind of iterating on best responses further and further would actually bias that much.
Great.
Thank you.